Howdy folks, welcome back to chapter 2. We're on lesson 3. Today we're talking about acceleration. What I do need you to grab, because you're going to see this show up in just a moment, I'm going to use in my notes the graph that we made a few lessons ago on this page of your notes, where we did a little calculation of velocity and we converted it into a velocity time graph. So when you see a little picture show up, it's going to be that picture. So if you want to find those notes, it'll help you out with today's. So we've talked about acceleration already. It's all about changing velocities. So acceleration is how quickly your change in velocity occurs. So an object with a big acceleration means it's going to change velocity quickly, and an object with a smaller acceleration means it takes a little longer for that acceleration to change. Another way you can think about it, how fast is the velocity changing? The quicker it changes, the bigger the acceleration. The slower it changes, the smaller the acceleration. So there's that velocity time graph from last day. We'll see that. We're going to work with it in just a moment. But before we even work with that graph, I want to show you a really nice equation that we can use to calculate acceleration. Remember, it's all about changing velocity and time. So the equation is really nice. It looks like this. And really, we've got two equations here, just sort of stacked together to look like three, but it's two different ones. There is acceleration equal to the change in velocity over time. And that works great if a question gives you the change in velocity, but quite often we have to find the change in velocity. And remember that the change in velocity is equal to the final velocity minus the initial velocity. And then you would divide by time. So this boxed equation, and I think it looks like that on your formula sheet, is actually two separate equations. And you pick the one based on what they give you in a problem. If they give you the change in velocity, then you would go with that option. And if they give you two different velocities, then you might have to go plug them into that equation. So I don't think you'll find that too difficult at all. Don't sweat that equation. We're going to see actually in just a moment that it's really, really nice to use. So here's what those things mean. Final velocity is VF. Initial velocity is VI. The other thing I want you to remember is, hey, we drew this line through the data points a few lessons ago on our velocity time graph. We said, hey, that object is accelerating. We knew that because we saw a nice curved displacement time graph as well. And I think you could probably figure this out. What could you measure about this velocity time graph, this nice straight line, that might give you some information? What would be easy to measure for that line? Well, slope would, because it's nice and straight. And it turns out if you measure the slope, if you pick 2 points on that line to make a slope triangle, notice we picked some nice points that are far apart from each other to make a nice big slope triangle. If you pick a couple of points and you play the delta t game along the horizontal axis, you can see delta t would be 3.5 minus 1 seconds. And on the velocity time graph, the delta v, that will be equal to 7 minus 2 meters per second. So if we take the slope of that line, turns out what you are measuring about that slope is the acceleration. You're going to get an actual value for how quickly that velocity is changing. So if you plug those numbers into your calculator, you're going to get an answer of 2.0. Remember, we want our 2 or 3 sig figs. 2.0 meters per second. And that's kind of weird, but it's actually a nice way to think about that. An answer of 2.0 meters per second tells you that the object is gaining 2 meters per second every second. So that means, assuming we start from rest, after 1 second it would be traveling 2 meters per second. After 2 seconds, it'd be traveling 4 meters per second. After 3 seconds, it would be at 6 meters per second. So that's how much velocity it's gaining every second. Now, it turns out mathematically we don't really leave the units like that. Meters per second actually turns into meters per second squared. And that might look a little bit strange. That might be a new unit to you. But what's really nice is that unit makes accelerations easily identifiable. Because as soon as you see meters per second squared, you can go, oh, that's a rate of acceleration. But really in our head, even though we see the meters per second squared, I like to think about it as meters per second, because it tells you that's how much velocity you're gaining or losing. If it's a negative number, you'd be losing that many meters per second every second. So there you go. The acceleration on that velocity time graph is the slope of the line. So if you're ever trying to get acceleration off of a velocity time graph, you don't necessarily need this equation. We kind of use that just for word problems. You want acceleration off of a velocity time graph, simply slope the line. Easy. Now, acceleration is a vector, direction matters. We'll see that in some word problems. Let's try out a few word problems. So the first one, what's the acceleration of a car that goes from 72 kilometers an hour to rest in 4.8 seconds? Now, first thing we're going to have to do, that number. Kilometers per hour does not play nicely with seconds. So remember a few lessons ago we chatted about the conversion to get from kilometers per hour into meters per second, and that was division by 3.6. So in this case we've got a car traveling at, let's say, 20 meters per second. And then it comes to rest. That means 0 meters per second, and that takes 4.8 seconds. We've actually got a negative acceleration, some slowing down, right? Because it started out fast and it went to skidded to a stop or slowed down to a stop. So what I would really suggest you do for these questions is make a little list of your variables, just so you don't get mixed up. And this is, I promise, not a make work project. This is a prevent you from making silly mistakes project, which is always worthwhile. So I like to do this VI, VF, AT, and I make that list the same way. I'm an old dog that's just used to that. So now we plug our numbers in. We don't worry about sig figs or units. But if we go and put numbers into that list, the initial velocity was 20 meters per second. The final velocity is rest, which is 0. Acceleration is what we're looking for, so that's a question mark. And our stopwatch said 4.8 seconds. So you can see here that we've got a separate VI and a separate VF. So I'm going to go with the expanded version of the equation, not the delta V version, but the VF minus VI. And we're going to plug our numbers in. You get an answer of, to 2 or 3 sig figs with units, negative 4.17 meters per second squared. Now what that means for the object is it's losing 4.17 meters per second every second. And that way, in 4.8 seconds, it's going to go all the way from 72 kilometers an hour to rest. Okay, here's example number 2. An airplane's accelerating at 6 meters per second squared. How long is it going to take, how much time, to go from 4 meters per second to 50 meters per second? So maybe this airplane is on the runway, they're taxiing down the runway, and then the pilots jam the throttle. And maybe 50 meters per second is the magic number before the plane can actually get airborne. In this case, no worries about units. We've got meters per second squared, meters per second, meters per second. Those will all play nicely together. So we want to go ahead and make our list of variables. Oh, sorry, don't worry about the equations here. All I did was I took this equation, A equals VF minus VI over T, and I've rearranged it to solve for, or just showed it rearranged with the VF by itself. This is another equation that we're going to see on the formula sheet later, but let's actually not worry about it for now. So let me do this. Let's make that disappear, because that's coming down the pipe. There, scratch that. Okay, plug in some numbers in. What's the initial velocity of the airplane? Well, it was initially going 4 meters per second. And then we reach a final velocity of 50 meters per second. This one's a little bit different. They're giving us the acceleration at 6 meters per second squared and asking for time. So we're going to want to go with the expanded version of the equation, which is this one right here. And we're going to plug our numbers in, and I guess we have a little rescue mission here. We have to solve for t. So it's 6 equals, and now I cannot, you have to be careful, right, that you don't get your VF and VI mixed up. And I can see here by making my list, I can be careful and say, okay, it's 50 minus 4 and not the other way around, divided by t. So mathematically, we need to solve for t. First thing I would do is actually tackle the subtraction, the 50 minus 4. I wouldn't worry about the t quite yet. So 50 minus 4 is 46, all divided by t. And the algebra now says if we want to solve for t, we can multiply both sides by t. On the right-hand side, it will cancel. That leaves us with 6 times t equals 46. And now we're a quick division away. Divide both sides by 6. That's going to give us an answer of, let's try this out, 46 over 6. 7.67 seconds. 2 to 3 sig figs and units. There's how long it takes that airplane to accelerate. So again, I'd like to think some basic algebra, get yourself organized with your list of variables, and off you go. It's really not too bad. So I'll actually stop there. Finally give you guys a nice short lesson. I'm sorry that some of these are getting long. What I'd love for you to try with this lesson for practice is worksheet number 3, which is, if I can pull it up, this one here. Hopefully you can see this okay on the screen. Give that a try. There's 10 questions for you. What I would highly suggest is on this worksheet, if you're looking at it or if you've printed it off especially, I would actually do the calculations on a separate piece of paper for most of them just to give yourself some more room. Please do make that list of variables, the VI, VF, AT, just to get yourself organized, and that way you won't make any silly mistakes. So give that a try. The answers are on the back of the Chapter 2 outline. They're also on the website. And if you get stuck, give me a shout. Fire me an email, come and see me, and we'll chat about it. Have fun accelerating.